we've got Be3N2, and we've got to figure out the percent composition by mass of this. So let's find for each of BEN for N. So let's look first for our percent of BE. And so to do this, we have to take the number of BEs, and here that's going to be 3. So we say 3 times the mass of BE, that's beryllium. So once again, get out your periodic table. And beryllium has a mass of 9.01. So 9.01, then times 100 to get into percents. All this divided by the molecular mass of the whole thing. Well, we haven't figured that out yet, so let's do that here. So 3 times the molecular mass of the atomic mass of Be is 9.01, and then we're going to add that to the number of nitrogen, so that's 2. That should be a plus sign right there. That didn't pick that up very well, did it? Let's erase that. I erased more than I intended it to. Let's try this again. So we have 3 times 9.01 for the beryllium plus my marker just isn't even working right now. I'm not quite certain why. We'll say a plus like that. That's really strange. But plus, we have 2 nitrogens. So 2 nitrogens times the mass of nitrogen. You look on your periodic table, it's 14.01. So 14.01, if we add these two up, then you say, once again, get out the calculator here, 3 times 9.01 plus 2 times 14.01. And when you do that, you get 55.05. And so 55.05 is going to be our molecular mass of Be3N2, of beryllium nitride. And so that means we'll use that over here. So 55.05 is what we have here. So just some quick math here shows that we have 3 times 9.01 times 100, and then divide that by 55.05. And so we find the percentage by mass of Be has to be here a total of 49.1% Be for this particular substance right here. Now, just as a quick note, for the purposes of this class, is that we will be rounding our percent compositions to the 10th place. And so this actually is 49.1008, but we are going to round to the 10th place, so 49.1 is what we get for our mass of Be. And so let's take a look at our next one. Our next one would be nitrogen. And so to find nitrogen, what we do is, well, the simple way is simply say, well, if Be was 49.1, then the percentage of nitrogen would have to be 100 minus that. 100 minus 49.1 is just 50.9. So we have 50.9% nitrogen. Excuse me. So these are the two we get for beryllium and nitrogen. 49.1% Be, 50.9% nitrogen. Our next one here is tungsten persulfate, I think it is. No, tungsten sulfate, WSO43. And so let's just get the first step, let's get one of the steps out of the way. Let's find the molecular mass of this thing before we even start. And so to find the molecular mass, we know we have 1 tungsten, so we have 1 times the mass of tungsten. And so a quick look onto your periodic table tells you that tungsten has a mass of 183.84. 183.84. And then we're going to add that to sulfur. Well, we have 1 sulfur in the sulfate, but then we have 3 of those total, so a total of 3 sulfurs. 3 sulfurs times the mass of sulfur, which periodic table says is 32.07. And then our last one here is oxygens. It's SO4, but there are 3 SO4s. That makes for a total of 12 oxygens. So 12 times the mass of oxygen, which is 16.00. So add all these guys up right over here. And when we do that, let's take a calculator out. And we say 1 times 183.84 plus 3 times 32.07 plus 12 times 16. And we get 472.05. So 472.05. That's going to be our molecular mass for this guy right here. So let's find what the percent compositions are for these different guys. Let's say we're going to start off here with tungsten. And so if we want to find the percent tungsten, we're going to say, how many tungstens do we have? Just 1. So 1 times the molecular mass of tungsten, or the atomic mass of tungsten, which is 183.84. We already discussed that, times 100. And we're going to divide this by the total molecular mass, which is 472.05. 472.05. Okay? And so from that, if we do the math on this, we say 1 times 183.84 times 100, and then divide that by 472.05. And by doing that, we get 38.945. That'll round us to 38.9. And so we know we have 38.9% of tungsten. Our next one we want to do, let's take a look at sulfur. So we'll say percent of sulfur. And so to do sulfur, we say we have how many sulfurs? We have 3 here. And so 3 times the mass of sulfur, which is 32.07. 32.07. And then times 100 to get into percent. Okay. Divided by the total mass, 472.05. And if we do the math on this, 3 times 32 times, 32.07 times 100, and then divided by the total mass, 472.05. Doing that, we get 20.381. That'll round to 20.4. And so we have 20.4% of sulfur is what this compound is. Our very last one is our oxygen. And so to find percent oxygen, we could just add those 2 guys up we had before and subtract it for 100. But let's go through this one and use it as a double check. So we have 12 oxygens total, and oxygen has a mass of 16.00, and then times 100 to get into percent again, divided by the total mass, 472.05. So let's see what we get. We say 12 times 16 times 100, and then divide that by 472.05. And so when we do that, we get, excuse me again, 40.67. That would, that would just be 40.7. 40.7, that's a 4%. And so this is what we get. So we have 38.9% tungsten, 20.4% sulfur, and 40.7% oxygen. Our double check is, say, 40.7, the oxygen percent, plus the sulfur percent, which is 20.4, plus the plus the oxygen percent, the sulfur percent 20.4, plus the tungsten percent, which is 38.9, and we add those up, we get exactly right at 100%. And so we know we've got this right. So this is how you go about finding percent composition by mass. Suppose we have a particular chemical which is 48.2% iron, 41.4% oxygen, and 10.4% carbon. First step that we have to do here is we are going to divide each of them. We got to convert them to moles. And so if we convert them to moles, the first step is basically to say these aren't percents anymore, these are grams, right? So we get rid of those guys, we got grams in their place. And so we got grams of each one of these guys. And so with those grams, we can now go ahead and we're going to divide each one by their molecular mass, or by their atomic mass. And so if we take 48.2% of iron, let's look up what iron's atomic mass is. Atomic mass of iron is 55.85. 55.85. The atomic mass of oxygen is 16.00. The atomic mass of carbon is 12.01. So let's divide all of these. And so going ahead and breaking out the calculator, we say we have 48.2 of iron, grams of iron divided by 55.85. And so when we do this, we get the amount of iron, of iron to be 0.863. And then for oxygen, we take 41.4, and we're going to divide that by 16, and we get 2.587. So we'll say that's 2.588. Okay. Then for our next one, we take 10.4 and divide it by 12.01. And for doing that, we get 0.866. Okay? And now remember our last step is we're going to find whichever one of these is the smallest and divide all of them by that. And so the smallest one here is 0.863. And so let's divide each one of these by 0.863. So 0.863 divided by 0.863 tells us, this just gives us 1, so I know that I have just one Fe, like that. Then our next one is 2.588, so I take 2.588 and divide that by 0.863, and when I do that, I get 2.9988. That's basically 3. So I know I have 3 oxygens right here. My last one is 0.866 divided by 0.863, and when you do that, you get just barely slightly over 1. And so slightly over 1 is going to be just 1 here, and so that was just going to be a C. So my empirical formula here would be FeO3C, and a quick look at this would say, well, which one has to be the cation? The cation is going to be probably iron here. And so that one should be out front just like it is. And so we have Fe as our first one. The other two, O3 and C, we know these have to be part of a polyatomic ion. So if you look at your polyatomic ion sheet, do you see any that have carbon and oxygen in them? And just carbon and oxygen. And looking at this, there are, I was thinking there were 2 of them, but I only see 1 right now. Actually, there are 2 of them. There is oxalate, which is C2O4. And that doesn't make sense here. And the other one is carbonate, which is CO3, and that would work perfectly. Sorry about that. Took my headphones off for a second. So the next one has to be CO3. And so then we have CO3 for the rest of this here. And that makes it perfect. That's just iron carbonate. It's iron, let's see, what is that? Iron 2 carbonate. And so this would be what our empirical formula is for this first one here. Let's take a look at the next one. We have 69.9% iron and 30.1% oxygen. And so for this guy right here, basically what we're going to do is, let's say we're going to first basically convert these to grams. And so what we said was that these percentiles just go away. They both turn to grams here because we're taking this out of 100 grams. We want to divide both sides by, or both these two things, by their molecular mass, or by their atomic mass. So 69.9 divided by iron, which we said before is 55.85. So 55.85. And then we're going to do the next one by oxygen. Oxygen here is 16.00. And so we got that here. So let's do the math on those two. Quick little bit here says 69.9 divided by 55.85 gives us 1.252. So 1.252 for the iron. 30.1 divided by 16 gives us 1.881. And now we got to look and divide both of these two by whichever one's smallest. The smallest of these two is clearly going to be 1.252. So we divide 1.252 by 1.252, and we divide 1.881 by 1.252. And so the first one here just gives us 1. Now 1.881 divided by 1.252, and we do that, we get 1.50. Now 1.50 is not even real close to a whole number. This is a case, and this will happen sometimes, where that you'll end up with a fraction in one of your two answers, and it's going to be pretty close to basically a very common fraction. In this case, 1.5 is 1.5. And so 0.5 is a half here. Sometimes you end up with ones that are close to like 1.33 or 1.67. Those would be like the 1/3 and 2/3. Or you may end up with something that's like 0.2, which is 1/5. If that happens, what you have to do is you have to scale this up until you get a whole number ratio. Since this is a 1.5, we're going to have to multiply both of these by 2. And so if we multiply both of them by 2, then instead of a 1 to 1.5 ratio, this becomes instead a 2 to 3 ratio. And so that's basically what we're going to get here. And so if it's a 2 to 3 ratio, then we have Fe2O3 as our empirical formula. Fe, iron, is going to be our cation, and so that means that this is our final answer, Fe2O3 for the empirical formula here.